Hey guys, and welcome to another video. My name is Amy Barr and I am one of the engineering lecturers at West Suffolk College and currently work at the STEM Innovation Centre. So today we're going to be looking at one of the conservation of energy laws. So let's get started. So guys, when we are looking at the conservation of energy, we want to understand the actual principles of that conservation. That's going to come from the fact that we know that energy can not be created nor destroyed. It can only be converted from one form to another. Examples of this would include a loudspeaker, for example, from electrical energy to sound energy. You could also have that in reverse when you're getting sound energy can also be converted into electrical energy. So this is really helpful when we are looking at things. We also want to consider though, when we are talking about mechanical energy, is that the energy possessed of a body or object is remaining constant unless the energy is being transferred from or to the body, or any mechanical work might be going on. So once we are looking at the mechanical work, this is in joules or Newton meters. If an object or a body possesses any energy, it is then capable of doing any work, and that includes you lot as well. So when we're looking at work, when done, a force overcomes resistance, which is measured in newtons. It is then able to move over a distance, which we are now going to denote as S. So we've got the equation work is equal to F times S. One thing we also need to remember is that we might have some resistances to overcome. These could come in the form of three different things. You've got friction, gravity, or inertia. These can all affect the resistance of the actual mechanical work happening. So when we're looking at energy, we want to look at two types of energy in this session. The first one being potential energy. Now, potential energy is the energy possessed of that particular body relative to a datum, so a set point. This is measured from the change that we've got in potential energy, and it can be varied by the weights and the change in height of that particular object. We also need to include any resistances that we talked about previously. So in this example, the resistance would be gravity. So we would need to include gravity also within potential energy. And then my second energy is kinetic energy. So kinetic energy is an energy that a body possesses by virtue of its particular motion. This comes when we're translating kinetic energy from a half times the mass times that velocity squared of that particular object. So when we're looking at these particular objects as a mechanical system, the potential energy possessed by a body is often used into kinetic energy and vice versa. So once we've got this, we've got our potential energy plus our kinetic energy is then always constant. For example, if we were looking at a car going downhill, we need to remember to include its potential energy, kinetic energy, but also its frictional resistance to calculate the total energy of that particular car. The way that we can do this is we can add them all together. So it's really simple. Potential energy, kinetic energy, and frictional resistance will all equal our total energy by that particular body or object. So guys, when we're looking at energy, we also want to think about things such as power. Power is really important. It is a measure of the rate at which work is done or the rate of change in that particular energy. Power is then therefore denoted as the rate of physically doing some work. The actual SI unit for power is watts. That is the average power over the work done. When we have a constant velocity, we can use this to work out our instantaneous power. This is really helpful later in this video. So for our instantaneous power, we have got our force used times the velocity. Remember, guys, that our power is measured in watts. So moving on to a quick example for you. In this example, I have got a cage which is being lifted of a particular mass of 300 kilograms. It is accelerating upwards from a rest to a particular velocity of 20 meters per second, whilst travelling the particular distance of 40 meters. Whilst it's travelling that resistance, it encounters a frictional resistance of 150 newtons. Remember that we need to use the principle of conservation of energy in this question. From that, we need to work out three things: the total work done, the force tension in the particular cable, and also the maximum instantaneous power that is being produced. So what we're going to look at first is recapping what are those equations we need to use for the principle of conservation of energy. So I've got those highlighted there for you. And also, guys, I always like to start a question with a schematic diagram. It will always help you further down the road of you trying to picture what you're actually doing from words into a drawing. So I've done that for you here. This really helps because the next part we want to do before we even begin to tackle the question is we're going to put down all the variables that we know. So we've been given our frictional resistance in our question as 150 newtons. I can then write that down. I now need to know S, and if you remember from previous, we are talking about our distance, the distance that is travelled by that particular object. And in this case, it is 40 meters. We then want to look at our velocity. Velocity is then given by 20 meters per second. And finally, m is our mass. And we know our mass because it's been given at the beginning of the question for 300 kilograms. I've then also just transferred that onto the schematic. So that helps us if we label the schematic with all of the information that we've found out at this stage. So I have broken this question into three parts. The first part, we are going to find the total work done of our cage. So to do this, we're going to establish the work done in different steps. Remember, previously, the work done is made up from three separate parts: the potential energy, the kinetic energy, and the frictional resistance that we might encounter. All I have now done is I've then given each section the answer to what it's denoted in its term. This will make more sense as we progress further. So the first section of our work done equation is potential energy. Now, looking at that potential energy equation in depth, we have got our mass times our gravity times our height. Now, we know our mass because it's 300 kilograms. We know gravity, guys, because I hope you remember that is 9.81. And we also know our height, which has been given as 40 meters. So from that, we can put it into our calculator and work out the potential energy that we are going to have, which just so happens to be 117,720 joules. Now, the next middle section of our equation is our kinetic energy. So our kinetic energy equation comes from a half times the mass times the velocity squared. So simply again, all we're going to do is we're going to plug the numbers in. We've then got 300 times 20 squared, which gives us 60,000 joules. The last section now is all that we need for our total work done, which is our frictional resistance. Now the question gives us our frictional resistance, yet we need to remember that this is happening over a particular distance. So we need to also times it by that distance because we are considering it. So we are simply doing our frictional resistance of 150 times our distance of 40 meters, which will give us 6,000 joules. The last part of the work done is just adding them together. So all we've got to do is add all of our answers that we've accumulated together, and we will then get our total work done, which is 183,720 joules. So moving on, the next bit is finding the tension that is in that particular cable. The first part that we are going to do to that is we're going to transpose the equation. The equation being for force, we are going to use our work done equation. Work done being force times distance. The easiest way to transpose this is to simply look at the value that you want to find and then divide each side of the equal sign by the other part that you don't need. And in this case, we are looking for our force. So what I can do is I can then look at the other part of the equation that I don't need, and I can then divide both sides by that. And in this case, it is distance. So I'm going to divide both sides by distance. And guess what? That means I can then cancel out any reoccurring elements. And in this case, that is distance. So I can get rid of him, and also I can get rid of him. That'll then leave me with my force on one side and my work done and my distance on the other, of which I both know at this stage. I know my work done from the previous slide, and I then know that my distance is 40 meters from our highlighted section that we did at the beginning. So the last part is we need to work out the maximum instantaneous power. And to find this, we can use the instantaneous power equation, which we covered earlier. That just so happens to be our power is equal to the force used times particular velocity, all of which we know. So this is quite a simple one. All we're going to do is our previous force used found on the previous slide as 4,593 times my velocity, which is given in the question as 20 meters per second, which is then going to give me my final answer of my instantaneous power of 91,860 watts. Remember the units. So guys, I really hope you enjoyed this really quick video on the conservation of energy. Please leave a comment and I hope you enjoyed this session.